All right. It is flashing. All right, so basically we have, as in the picture of the situation, we have this wheel with a rod attached to it. And I guess from your point of view, all right, so it's like there's a rod over here that's going to come zipping around. That rod is going to detach and smack into object A, which even though it looks like a sphere there is a massless invisible box just so that the rod can smack into it like this, and we not have to worry about, where does the rod actually hit? Is the rod going to start twisting? I don't want to worry about that. The other conceit is that I have A already spinning, so when it gets to the top of the ramp and is about to come down, that we already have the perfect amount of spin on it so that it will continue to roll perfectly once the friction is acting on it. Obviously, not a realistic situation, but realism is way too complicated. So we'll start with wheel, rod, D, so I have D right here, I have A right here, and this is attached to A. So that's basic setup. In here, and for the fans at home, yeah, it's probably not going to help you a whole lot because the people who are in the class, there is access to this. Okay. Yeah, and as well as you have a picture right here. It's on Blackboard. All right, so the first bit is all about the moment of inertia. We did something like this very similar in class, find the moment of inertia of the whole thing. So the large disk, start out with the large disk. We're dealing with a disk. The moment of inertia is 1/2 mr squared. And the large disk has a mass of 10 kilograms and a radius of 1.3 meters. And so just simple plug and chug right there, and I believe it's 8.45 units would be kilograms meters squared. That was A sub I. Double I is the moment of inertia of the small disk. Well, again, it's a disk. It's 1/2 mr squared. And in terms of the test, that information is right there on the front page. And so this is 1/2 times a mass of 4 kilograms times a radius of 0.5 meters squared. And so we end up with 0.5 kilogram meters squared. And then the thin rod. My recollection is that the first time I gave this test, this is where a number of people missed an important piece. If I have a thin rod, the moment of inertia is 1/12 ml squared, and a number of people just plug and chug into it. But that's only if the thin rod is rotating about its own center. So because that is not rotating about its center, this rod is rotating about this point right here, we have to use the parallel axis theorem. So the formulas are usually about rotating about its own center. Sometimes they will do slight variations of that. However, in this case right here, we definitely have to use the parallel axis theorem. So the moment of inertia will be in about its center of mass plus mh squared, where h is how far it is from the center of the rod to where it actually is rotating. So this becomes 1/12 times the mass of the rod, which is 1 kilogram, times its length, 0.2 squared, plus, well, how far did it move? Well, it went from here, and we can go for the typical stunning effects. So it's going to move this far right here, which is half the length, so that's 0.1 meters, plus the radius of the big wheel, which was 1.3 meters. And so the mass is still 1, and the distance that it moved was 1.4 meters squared.
Is it 1/2 or 1/12?
It should be 112. Thank you. That 1/2, 112 thing, I remember in 8th grade making that mistake too. Why that stands out of all my mistakes in 8th grade, I don't know, but been doing that one a while apparently. And I got 1.963 repeating kilogram meters squared. So I have these 3 objects that are all rotating, small disc, big disc, and this rod, that are all rotating about the center. And so the last question is, what's the total moment of inertia about the whole thing, Well, I got the pieces, just add them up. And so there's the moment of inertia bit. Linear acceleration of d. So now we get into basically a pulley system. If I look at the forces involved, I have d, where I have its weight acting down, and there's a tension acting up. I've got this system right here, which is rotating with a tension acting down. And then there's something holding it up, some bit of magic holding the pulley system up. But ultimately, I'm not going to care about that one. I'll just call it Y for no, why not? So when I'm trying to figure out the linear acceleration of d, I'm basically doing Newton's laws. This is the stuff that we did in chapter 4 and 5, except we're throwing in rotational motion. This is not centripetal motion, this is rotational motion. Because we're not dealing with the forces required something to travel in a circle, we're dealing with basically the forces involved to get this to rotate. So I have my 2 equations of motion. I have F equals ma. Let's make down positive. So this becomes W minus the tension is equal to the mass of d times its acceleration. I don't know tension and I don't know acceleration, so I have 2 unknowns, so I need 2 equations. The other equation's coming from here. And so I bring in tau is equal to I alpha. Technically, these are vectors here. Since I'm making down positive for d, in other words, this direction is positive, so that would make that force positive. I'm going to go ahead and it's going to cause this wheel to rotate counterclockwise, thumb pointing out, so I'm going to make outwards positive. And so my other equation is that the torque, which is the force, because it's perpendicular here, the force times the radius of the small disk, because that's where the force is being applied, which is 0.5, is equal to the moment of inertia of that contraction, which we just calculated, times alpha. That is the angular acceleration of this disk. Assuming that there's no slipping going on here, there's a relationship between the acceleration of d and the angular acceleration of the wheel. And so that should be that, well, I know that V is equal to omega r, A is equal to alpha r. And so I'm working with my 2 equations here. So mg minus the tension is equal to mdA, and do R sub S for small times the tension is equal to I times alpha, that's A divided by radius small. I know I plugged in numbers and then I stopped, then I took them out, but these are the equations I'm working with here. This is the mass of D, which is given, should be, there we go, 15 kilograms. So this is 15 times 9.8 minus my tension is equal to 15 times its acceleration. And then 0.5 times my tension is equal to 10.913 repeating times acceleration divided by, it should be 0.5, yeah, 0.5. Two equations, two unknowns, however you want to solve it. Ultimately, we want to know A. So I'm just going to solve for, so many ways of doing it. Let's just solve for tension in the first one. No, I really don't care for that. What I'm going to do is I can multiply this first one times a half. So 7.5 times 9.8, whatever that is. Someone could do 7.5 times 9.8. So I get 73.5 minus 0.5 tension equals 7.5A. That's this first one. The second equation, I get 0.5 times the tension is equal to, that would be, let's see, 0.6 repeating, or 6 repeating, 2, 8 carried 1, 21.826 times A. Basically, that divided by 0.5. Now, if I add the two equations together, my tension pieces, the tension terms cancel out. So I'm left with 73.5 equals, that's 2, 6 repeating, 3, 29.326 repeating times the acceleration. And so the linear acceleration of A is that's part B, 2.506 meters per second squared. Assuming I copied things down correctly, have made careless error again. So that's the answer to B. Now that I know A, for part C, what's the angular acceleration of the disks? Well, I have the relationship already right there. I'd already made that substitution. I know that the angular acceleration of the disk is equal to A divided by R, which is 2.506 divided by 0.5. So 5.012 radians per second squared. That's the answer to part C. Part D is the angular velocity, angular speed I asked for. Angular speed of this when the rod gets down to here. When I say 270 degrees, that's 0 degrees, 270. This is just a constant acceleration problem. Let's see, we don't need this information anymore. I know that my initial angular velocity is 0 radians per second. The angle through which it's going to turn is, we're doing radians, 3 pi over 2 radians, or 270 degrees. Omega final is what I'm trying to find. My angular acceleration, we just found, that's the 5.012. And actually I do have another decimal point written here. 10125 radians per second squared. And so we're using the formula that doesn't have that doesn't have time in it. So you know them, you're good. Otherwise, you look on the front and you scan until you find the one that you need, which is not on there. So I need to remember to make sure it's on the newer test. So omega final squared equals omega initial squared plus 2 alpha dot delta theta. And so that's equal to 2 times 5.0125 times 3 pi over 2. And you end up with omega. That speed, when that rod is finally, the angular speed, when it finally gets around to there, is, this is D, 6.8733 radians per second. He asked for the linear speed, so now we're popping over to V equals omega R. So that was D right there. EV equals omega R. I know what omega is. The trick is R, because R is not the radius of the small disk. Because we're talking about the center of the rod here, this. So the radius is from here to here, which we already did. It's 1.4 meters. So V is going to be equal to 6.8733 radians per second times 1.4 meters. It's how far the center of mass is, and I specifically say in the problem, center of mass, how far the center of mass is from the axis of rotation. They get 9.6226 meters per second. And then we have a perfectly elastic collision. So I don't need this information anymore. Right there. So I have a rod of mass 1 kilogram. So basically I've got this rod, mass equals 1 kilogram, traveling at 9.6226 meters per second, about to glide into ball A, which is a mass of 3 kilograms, in a perfectly elastic collision. And this is why I put the invisible box around it, so that when that rod comes around, it will hit flush in with the box. Now this perfectly elastic collision, it's one-dimensional. There's 3 techniques I did. I'm going to do technique number 3 right here on the board. And I know not everybody is going to choose that, but that's just the way I'm doing this one right now. So we have rod and A. So this is going 9.6226. This one's going 0. This is in the lab frame, or problem frame. And then we need to shift into the 0 momentum frame. So I need to figure out what, if it were perfectly inelastic, what would collision, what would be the final momentum? Well, it's going to be 1 times that, divided by the total mass. So whatever that number is, minus 2 point, what is,
2.40565.
so I subtract that, negative 2.40565. And that puts me in the zero momentum frame. And so, well, this one I can do, minus 2.40565. And this one is going to be roughly 7.21. 216195?
Yeah. Wait, 695.
695. Okay. So that is the collision just before the collision in the zero momentum frame, and then they collide. And the advantage of this is here's the math for the collision. So I just switch signs, 695, and then plus 2.40565. And then I shift back into the problem frame. So I do the opposite of what I did over here. So now I add 2.40565 plus 2.40565. And the question was, I think, just how fast A was going to be going. So it should just be the sum of those two things. And 4.8113. And there could be some rounding differences depending on how you do it. But that's what I had written down here. Meters per second. So that is the answer to F. G. A is spinning around just the right amount so as to simulate perfect rolling on the platform. What's the angular speed? Well, I know what the linear speed is, and I'm trying to figure out what is the angular speed. And so to simulate perfect rolling, I'm going back to V equals omega R. And so omega is V divided by R, which is 4.8113, divided by the radius of ball A, which is 0.1 meters. And so I get 48.113 radians per second. H, the linear speed of A at the bottom of the ramp. So I have a ball that gets to the ramp. The ramp has friction, as is written in the problem here. So basically, we're dealing with a conservation of energy problem.